kind of working on, got it. So it's really open-ended. So we've been doing a lot of grant-based work, which is basically, NASA says we have these interests broadly. We want ideas and technology development that applies to these interests that we think are, going to be missions possibly in the next 10 years or 20 years or however far out the line. And then they leave it up to the investigators to kind of
interesting.
sell an idea. Like, we're going to work on this. We're going to do these environments. We're going to do this. And it's going to advance the cause in this way.
So they don't really constrain you. You set your own bounds in a way.
Not at this level. Now, once you get to the actual flight hardware, which is assembled in a NASA center clean room, generally JPL in Pasadena, California, then those have very strict protocols and test standards and radiation hardening and temperature cycling and all of these things that qualification process requires for anything that's actually going into space. But here we're really at the base level of some of these technological questions, like how are we even going to approach this thing? That's kind of, to me, is the funnest part to be. So
do they take some of your modules and then ruggedize them, so to speak, according to their own spec?
Yeah, that would be the idea. So as we're eventually moving, the stuff we're working on would not even begin to be considered for launch until the late 2030s. So in between now and then, our goal is to get up to flight capable systems, and then it would be assembled in a facility much larger than this, according to those, and there's sterilization, all kinds of planetary protection protocols that have to be met to make sure we're not contaminating other worlds with Earth stuff. So yeah, that all happens at kind of at a different level from what we're investigating at the grassroots here.
Great. Well, we're just coming up on 25-2, so maybe I'll just say a few words. I see we have 27 people signed in, and I think some more people are arriving. So we have a guest speaker tonight, and then I think our president would like to say a few words, correct? Yes. And then I have something from Edmonton for Dave, and Dave Payne has some items to share depending on how the time's gone. So, and does anybody else have anything for this evening?
Chris?
Yes, Dorothy.
Randy willing, I might could say a few words about especially judging it for the science fair.
Oh, right. Yes. Okay. I'll add you to the list.
Recruit some new, but just a few words, not long.
Yeah. Sounds great. Very good. Okay. So it looks like the number of people arriving is slowing down, so maybe we should get started, especially as Vickie is 2 hours ahead of us, so it's getting late where she is. So I'd like to start off first by thank Jeff for arranging to have a guest speaker tonight, and now I'll turn it over to Jeff to introduce Vickie.
Thank you. I'm going to just do a quick screen share if I can get this working. Super. Okay, so Stone Aerospace has been in existence for about 15 years. This organization is focused on approaches to the exploration of ocean worlds in the solar system with prototypes in the Earth environment. Ocean world exploration involves penetration of layers of ice and then autonomous exploration of the water world with possible added challenge of sampling for biosignatures of life. Autonomous ice penetrating robots are called cryobots. In association with NASA, Stone has developed and field tested several generations of cryobots. Autonomous vehicles for exploring and mapping worlds are called AUVs, or autonomous underwater vehicles. In the past 6 years, Stone has developed and field tested at least 2 generations of AUVs. Our speaker tonight from Stone Aerospace is Vickie Siegel. Vickie's worked with Stone, well, since the beginning of the company, since about 2005. She's a system designer at Stone Aerospace, and she's also the director of robotic field operations. So tonight, hopefully, she'll be able to touch on ocean worlds in the solar system, the overview of some of the prototype systems that Stone has built in association with NASA. And if we have time, touch on some of the technology problems, both overcome and anticipated. So Vickie, I will turn this over to you.
Thank you. That's an excellent intro, and I'm glad to see that my talk is on point here. So let me see if I can go back to sharing. You guys got that screen?
It's good.
Okay. And just, you know, I can talk forever, so don't hesitate to jump in and wrap me up if I'm going too long here. Because when I've got the full screen here, I don't have my little clock in the corner anymore. So I'll try to keep on time. And I'm also not a very formal person at all. So if anyone has a absolutely burning question that comes up in the middle, please don't hesitate to just jump in and let's have a conversation. But thank you so much for inviting me to talk. It's kind of a neat thing now that we've all gotten used to more of these Zoom meetings to interact with these groups that I'd never get a chance to interact with otherwise. It's really kind of a neat side thing here. So yeah, so I'm going to talk about robotics for the ocean worlds. Let's see. Yeah, so just a quick background on Stone Aerospace. Basically everything that Jeff said. Sorry, I've got a lab kitten here and she's very riled up being late at night. So we might see our lab kitten pop in the screen here. But anyhow, so Stone Aerospace been around for about 15, 16 years. And our whole goal is to do stuff that is fun and awesome to us. It's a really unusual company based on developing technology, prototype technologies for NASA planetary exploration. And typically we're looking at Europa or ocean worlds. And so what is an ocean world? Very basically defined, it's any kind of body in the universe that has a liquid water ocean. So there are several in our solar system, and the harder we look, the more of these we find. So Earth, of course, is an ocean world. Europa, Titan, Enceladus, these classic ones that are becoming more common knowledge among lay folks as being ocean worlds. And this slide, for a while, I've been using kind of the image on the left here as my ocean world slide. And I was updating the talk today, and I was like, you know, there's Pluto and Ceres aren't on here, and I should actually probably update this slide. And so I was surprised to find that there are also these smaller satellites of Saturn and Jupiter are now potentially considered ocean worlds as well. So this is something that even within our own solar system, we still don't even know entirely what we're dealing with. It's really exciting, cool stuff. Most of what we've been looking at is technology for Europa, which is the 6th moon of Jupiter. It's one of the original 4 Galilean moons. It's similar in size to Earth's moon. It has an ice shell that is many kilometers thick, maybe 30 kilometers thick. It has a liquid ocean and it has a rocky core. We believe that we've observed plumes, ejecta, coming out of these things actively. And this is a place that's really an exciting target to look for possible microbial life off of Earth. And one of the reasons that folks fixate on Europa is because the ocean has interfaced with 2 different other systems. So there's an ice water interface, and then there's a water rock interface. And life really likes gradients and interfaces. And these are places to look for. And that's kind of part of what makes Europa very intriguing. So when you look at a mission to explore Europa, what do you need in terms of robotics, other than the spacecraft that gets you there, which is a whole other story? Basically, you need a lander. So, you know, NASA, particularly the Jet Propulsion Lab, has gotten very good at these. You know, the Curiosity and Perseverance rovers have landed with the crazy sky crane thing. They've really started to dial that system in. It'll be something similar that goes to Europa, probably. It's still going to be very rough terrain to land something on the surface of Europa. Then you need a cryobot, an ice penetrating robot, to get through that shell. And then once you get through the ice to where your real target is, that ocean, then you need an autonomous underwater vehicle, basically an underwater version of a Mars rover that can swim around and map a place without human guidance and without any other kind of external navigation aid at all, which is actually a much tougher problem than what's occurring on Mars currently. So I'll start with kind of our work in cryobots, and there are many different ways to try and approach this problem. And we've come at it from different angles over the years. So I'll just kind of highlight these three projects that we had: Valkyrie, Archimedes, and Thor. The first question when you're talking about a cryobot, no matter what approach you're taking to getting through the ice, your first problem is power. And spoiler alert, it's going to have to be nuclear. So solar power that far out is not going to be sufficient. Primary batteries are not going to be sufficient. When you think about the amount of power to get through 30 kilometers of ice, whether you're drilling or melting or what, it's a lot of power, and it's going to have to be nuclear. Now, I am not a power systems engineer. I'm not a nuclear physicist by any means. There are many ways to do this. This slide is just to show you that they exist. But for our purposes right now, we still need to solve all of the other technology questions that surround cryobots and how they could potentially function in those designs to make sure that they are ultimately relevant to when there is a thermal source. We need to come up with some clever ways to kind of fake having a thermal power source. We can't just plug this into a generator and call it a valid cryobot, because we're not going to be getting electrical power to run this system. Whatever it is, it's going to be thermal power. So we've come up with a couple ways to create some clever surrogates for a thermal power source. And the first one of those actually used a laser in the Valkyrie project. So this cabinet that you see in the rear of the photograph, it kind of looks like a refrigerator, is actually a laser that's generating 5 kilowatts of laser power. And we actually sent that 5 kilowatts, which is a high powered laser, it'll cut through an inch thick steel plate. We sent that amount of power over a very thin fiber optic thread, a thin glass waveguide. Basically, the way this worked to simulate a thermal source is that we had that laser cabinet off on the side. The laser light goes down through that fiber and it enters the cryobot. So this is our prototype cryobot. And down the black section down towards the end is actually kind of a double-walled heat exchanger. So what would happen is the fiber would come into the rear of the vehicle. The laser light would exit the fiber and go through a series of optics that would spread the beam very evenly over the cylindrical walls on the inside. That cylinder, the cylindrical walls, is actually a heat exchanger. So you're heating up that cylinder. Meanwhile, we're taking meltwater from the ice, running it through that heat exchanger, heating up the water, and then jetting it back out the nose. So if you see on the right, that silver plate has a bunch of holes in it. The centermost one is actually a jet that's pumping hot water out of the nose, heated up by the laser, out of the nose, into the ice. And actually hot water drilling or hot water jetting is the most successful and most commonly used way here on Earth to create very deep holes in Antarctic ice and in Greenland for things like neutrino observatories, the IceCube project, if anyone's familiar with that. So hot water jetting is the way to go. And we found a way to do it with a surrogate thermal source. So we actually deployed this system to the Matanuska Glacier in Alaska. And this is about two and a half hours northeast of Anchorage. And we were there in 2014 and 2015. So that white tent you see was kind of our mission control, where we're watching everything happen. The gray tent had the laser cabinet and the laser chiller. You can see the big generator next to the gray tent. You can see the big gantry. You saw how tall that cryobot was. And then on the right, you can see Bill Stone, the company founder, and then one of our electrical engineers kind of watching as the tail end of Valkyrie kind of goes down the hole. One thing Valkyrie was able to do was steer. So you saw that jet on the center line, but there were also 4 additional steering jets that were offset from the center by about 5 inches. And so by differentially, jetting with one or more of those, you could actually steer the cryobot as it went down. And this is a behavior that we think we want to have on Europa if there's some sort of obstacle in the ice, some sort of foreign debris that we need to move around, or if there's something that we're looking ahead with ice penetrating radar and we say, oh, wait, there's a weird lens of water in all of this ice. We actually want to investigate that. Maybe we want to target something. So we were able to show some steering with a long cylinder, and that's kind of the trajectory you see in that plot. Valkyrie, most of the projects we have also carry this requirement with NASA, not to only develop technology, but to also gather some sort of terrestrial analog data for active astrobiology or microbiological studies here on Earth. So in this case, I'm not a biologist at all, but what I've learned many things in all of this work. And one of those things is that there's actually microbial life. There's actually little critters living in the interstices of the glacial ice. And so that was something we're like, well, that could happen on Europa too. Let's see what we can do to learn about that. And we've got all this meltwater. Why don't we look at it? And so this system had a cytometer on it, a microbial cell counter. And whenever the cell count would spike, then we would take a sample or take a filter sample. Okay. With all of that like laser surrogate, thermal surrogate work, we got really comfortable working with lasers. And we started to wonder, like, are we making this too difficult on ourselves? And what if we just go for the supervillain approach and just shine the laser itself like right into the ice? And there were several reasons that we thought that wasn't going to work. We thought it would reflect, we thought it would flash melt the ice and the probe would be ejected. And actually there's a slight difference between at particular wavelengths of laser light, ice absorbs the power slightly better than water does. So it's actually melting the ice as it goes and not ejecting the probe back out of the hole. So we were surprised to learn this and get to play with it. Really simplified kind of drawing here. It's a similar concept though. You have the fiber bringing laser light into the probe. Again, the light is exiting through a series of lenses, but this time, instead of heating up the side walls of the cylinder, it's going through a final lens that focuses it down below the probe and allows it to descend. And the easiest way to do this, hopefully videos will play well through Zoom here, but you'll see a purple flash that's actually not visible to the human eye. That's something that the camera is picking up, but it was actually pretty cool to see this thing in action. So this is sped up slightly, but if we were to run this for, at this speed for a long time, it would be the fastest cryobot on Earth, 22 meters an hour through temperate ice. So that ice block that we were working with in that video is something called a shot block. I guess they use these for parties. They use them to make ice sculptures. I think you can like melt little things, or you have like vodka shots going down. I don't know what they're really used for, but we buy them to test cryobots with. And one thing that we kind of eventually had to face up to is they make really pretty videos, but they're actually probably not very realistic, right? The ice on the surface of Europa is not going to be beautiful, clear shot block ice. It's going to have contaminants in it. It's going to be irradiated by radiation coming off of Jupiter. And it's going to be pretty mangled. And so once you start to really dig into this question of what the ice shell looks like, you can see there's actually several different like sub-regimes or sub-environments that a single cryobot is going to have to tackle as it goes down. So the first is the starting problem. The surface of Europa is incredibly cold and it's at a complete vacuum. It's also seeing some really heavy radiation depending on where you are on the moon. As you descend past the surface, you get into the upper ice is believed to be very brittle. It's fracturing, it's faulting, it's shearing, it's behaving in a very brittle fashion. Further down, you might have obstacles to avoid or things that you want to target. As you get lower, so this whole thing is a gradient, right? You go from the extreme cold surface temperature of Europa, which is 77 Kelvin or something, down to the temperature of liquid water. Under a bit of pressure. And so you have the ice represents that entire gradient. So you go through that brittle phase and eventually you get to a point where as you're warming, as you approach the ice, or as you approach the water, you're actually getting, we think, ductile movement, convective movement in the ice. It's going to be kind of stickier. It's going to be a completely different animal. Then eventually you'll break through from the ice to the water. What happens at that point? Do you just plummet down to the bottom of the ocean? Hopefully not. Hopefully you think that one through, right? And finally, you're exploring the ocean. So talking about what we do to kind of explore some of these environments, we really wanted to work more with that starting problem, that surface of Europa problem. What's it like when it's incredibly cold and it's under a vacuum? And so we built this cryo vacuum chamber. We call it Europa Tower. It can hold a block of ice that's about 2 meters high and 3/4 of a meter in diameter. we can take that down to 77 Kelvin and we can pull a vacuum on it that's 10 to the minus 3 torr. And so we took all of that and we took our little laser light probe, updated it a little bit, and we were curious to see how's that going to perform in an environment like that. And you can see my little Lego guy in there for scale. So again, this is sped up, but you'll see as the probe warms a little bit, even just with the light going into it, the frost flakes off, it starts to descend. The material that you see accumulating behind it is actually sublimate. So as the ice is being struck with the laser, it's actually not really melting, it's sublimating, it's going straight to vapor, and so that recrystallizes and forms behind that hole. Eventually it closes that hole off entirely behind it, and once you have it closed off against the vacuum, you can actually generate enough pressure to create liquid water, and then you can move into your hot water jetting phase, which is where you really want to be. So we did some experiments along those lines, and then more here in the lab this week. Pretty cool stuff.
Can I ask a quick question?
Yeah.
How much ice are you talking about?
For in the chamber, or?
Well, if this is, are you talking about a few meters of ice, or are you talking about 1,000 meters of ice, or how much ice?
Yeah, so on Europa, it's somewhere between, and there's all kinds of different modelers have different theories, but they think it's going to be between 14 kilometers and 30 kilometers
Of
ice for the shell. Now, there might be some weird places where there's been some like convective stuff come up. There might be some brine pockets and stuff that allow thinner sections or allow liquid water kind of like sub lakes or lenses trapped within the ice column. This is something that we're going to learn a lot more when Europa Clipper starts sending data back in the 2030s.
I'm just wondering if you're tapping into drilling technology, because I mean, you can get stuck, you could have a power failure, and now you don't have weight on bit, you don't have, you know, there's a whole bunch of challenges. What if you encounter a pressurized system?
Yeah. So there's a lot. We're in the early days on this stuff for sure. There are groups who are working with mechanical drilling systems. Honeybee Robotics in California is a big one. They've done a lot with mechanical drilling systems on Mars as well. The reason that we've stayed away from that is that our kind of general engineering sense is like it's such a long duration problem. 30 kilometers is a long way for your drill bit to dull up, for you to have some sort of mechanical failure. Also, you're dealing with this weird question. You have to melt everything anyway, because you're drilling down, and then you have your chips, right? Your drill chips have to go somewhere. And there's an enclosed volume behind you, above you, that they have to fit in. They have to fit just as well as when you dug them up. And that's a different situation from what you would have on Earth. So then there are groups who are like, oh, well, we'll melt the chips and then recompact them up above us as we descend. There's just no easy answers on this stuff. And I think ultimately the real system will be a combination of some sort of thermal, maybe some laser, maybe some mechanical. It'll be interesting to see what ultimately happens for sure.
Yeah, cool.
Yeah. So Thor is kind of the last one that I'll leave with on the cryobot stuff. Here, we kind of wanted to get back towards doing work in the field and seeing where stuff, you know, where basic ConOps work or fail in the field. So the idea with Thor was to create a Europa scale, a real true size thing that could run off of existing nuclear power sources that NASA owns. Again, we had to work with a weird surrogate system. So we came up with a clever thing here. Instead of using laser light to generate our fake nuclear source, we actually generated something called hotshot. And basically this is a big heat exchanger that is heated by a novel kind of resistor. Basically, we're running alternating current through a resistive fluid, and that actually causes the fluid to heat up. This was all super experimental, but you run current through a fluid, the fluid heats up, that fluid gets pumped through a closed loop in a heat exchanger. You're taking melt water in an open loop in the heat exchanger, heating it up and then jetting it again. Similar to Valkyrie. So this is a complete system. We've built this COVID derailed our plans to take this to Alaska before the project had to close out. But we're hoping to get follow-on funding to take this to a ice-covered volcano in Iceland, and then actually enter a subglacial lake for the first time with the cryobot system. So, okay, switching gears sorry, this is kind of this presentation is always a wild ride. So switching gears into autonomous underwater vehicles. Once you enter that ocean, again, you do not have any kind of navigation aid. So Stone Aerospace, this is actually the founding of Stone Aerospace, was this first autonomous underwater vehicle, AUV called DepthX. And the whole point of DepthX was to take it to a series of flooded sinkholes in northern Mexico. And this is kind of where I got involved with this work. I was telling some folks earlier, I know how to do work in Mexico, and so that was an aid. Basically, so this is Cenote Zacatón, and there were actually a series of 4 of these sinkholes, all kind of in a row. Again, this was an interesting analog environment for astrobiology studies because it's sulfur-rich water. These are thermal springs. So not only is it an interesting robotics challenge to navigate in a space like this, but it's also an interesting microbiological study site. When we built this vehicle, we wanted it to be an all-seeing eyeball, basically. So all the rays you're seeing here are sonar beams shining out, looking in every direction, so you can move through this sinkhole and see not only ahead of you, but also, how do I get out? What's behind me? What does it look like if I turn around? I think we've all walked into a room and then turned around and it looked maybe different from what we expected. So the idea was to navigate in a 3D environment here and look for life. This is just kind of a different rendering of those sonar beams striking the yellow walls. So I'll show a video here. What you'll see are these, oh, sorry. The music plays. So what you're seeing is the yellow cones are sonar hits going off under the walls. The red lines that you're seeing are places where the sonar has struck the wall and has returned to hit. So as we're descending into this water-filled sinkhole, we're seeing the really unusual geometry of this thing kind of being returned to us. Now, DepthX only had a couple of directives in this. It was, don't get closer than 5 meters to a wall, don't run out of battery, and when you get to the bottom, come back. So that was kind of like the most interesting looking one. And then Zacatón, the largest of the sinkholes, kind of very famous amongst the cave divers of the world. If you want to go down a rabbit hole, Zacatón is an interesting one. And right down at the bottom, you can't quite tell if it closes off or not. DepthX was too big to go down and investigate close on that. DepthX also had some of that science autonomy behavior. So, you know, we as humans can look at something like this underwater and say like, oh, there's sulfur in this water. And that stuff, I'm not a biologist, but that looks like goo. That looks like that might be alive. I can see something that looks like rock, but then I see this other stuff that looks like some sort of microbial match. And the trick is, how do you get a robot to come to the same conclusion? DepthX had a series of behaviors where it was constantly logging the water chemistry and the water temperature as it descended into the sinkholes. And if it found a chemocline or a thermocline, it would stop at that elevation and follow that chemocline horizontally until it's hit a wall. It would approach the wall, it would scan with machine vision, looking for a color change. And if it found a color change, like that red goo that we just saw, it would stop, it would take a photo, and it would grab a sample. And those samples that came out of there resulted in the discovery of several new divisions of bacteria. And there are people who get really excited about that. So coming out of that project successfully, we wanted to continue this complex mapping work, but we wanted to be working under ice because, of course, that's more similar to the actual Europa environment. So we teamed up with a limnologist, a lake geologist who's been working in Antarctica for a number of years. And we came up with this target to explore and map and document the 3-dimensional water chemistry of a place called West Lake Bonny in the McMurdo Dry Valleys. So this project was called Endurance. It had a nice long acronym for a name, not important, lots of people involved. Basically, we kept the same chassis, the same navigation brains, the same battery system from DepthX, but we swapped out that sampling arm payload for this instrument sonde. So the idea here is that we didn't want to churn up all of the stratigraphy in the water column in this very special isolated lake. Instead, we wanted to move the robot right along the top, and then just drop a single instrument sonde up and down as we navigated from point to point. So this is that sonde package that went in there. Working in Antarctica is always incredible. There's usually helicopters involved. We slung our precious robot on the bottom of a Bell 212 and sent it out. We built a tent over top of it. We drilled a hole in the ice. You can see that sonde is being lowered into the water right now for calibration prior to a mission. And then coming back to this satellite image here, this is a summary of all the missions we ran with Endurance, and every green dot you see here is a place where the robot paused and lowered that instrument package and charted the changing water chemistry throughout this lake. This is a place that scientists have been studying for 40 years. But the most they'd ever been able to do is, get out their little ice fishing, jiffy auger and drill one hole and send one little line down to get one depth measurement, maybe grab a couple samples in that one spot. And then they had to go back to the station. And so we were able to, in the course of 2 seasons, completely map the bathymetry of this place that's been studied, but not well understood for years. Another thing they wanted to see was what the glacier tongue looked like as it entered the lake. So I'll go back for a moment here. In the lower left, kind of where it says A, B, C, D, E, F, G, that's the toe, the terminus of Taylor Glacier coming down the valley, and then everything off to the up and to the right is the lake. So they were really curious, like, what does it look like where the glacier is coming into the lake? Where's the grounding line? Where's the point where the glacier is still sitting on the ground versus where it's floating? And so we were able to get sonar mapping of all of that. So right now we're looking at like a cake slice. We're looking at a profile view. If we cut into it and looked in from the side, what that looked like. So after,
Vickie,
yeah.
when the vehicle's doing the mapping, is it doing it in real time and sending the signal, or does the vehicle come back and then the data is read from the vehicle?
Both. So the vehicles are operating autonomously. They're doing their thing. We send them with their instructions and they figure it out. We do, in most of these operations, we do keep, and you'll see Bill's got it in his hand here, a very thin fiber optic data tether attached, because these are prototypes and we want to see if they're doing what they should be doing and what we think they should be doing. And it allows us to intervene if we want to or if we need to. So in these cases of running these science missions, this is actually a really powerful tool, because more than once a limnologist or microbiologist has been watching the camera feedback and say, wait, can we pause the mission? I want to go back and look at that thing again. Can we stop for a second? And so it allows, as we're trying to develop towards science autonomy, there's still a lot that we don't have yet, that human eyes, the human brain just latches onto that the robot doesn't yet. So that fiber is something that allows. So we're getting a data feedback of like a decimated data set. So a sparser point cloud of the geometry that we're seeing, low resolution camera. Most of it's all stored on board. And then when we retrieve the vehicle, it's a big data dump at the end of the day to get the high resolution data out of it.
Would it be tethered if you were using it on another planet?
Probably not.
Probably
Yep,
not.
probably not.
How would you
Hard
get
to
the
say. It's
data back?
possible. It's possible. It limits your range, right?
Yeah.
So
Yeah.
it depends on kind of what your con-ops are.
Yeah.
So the idea was just, again, bigger and better. We wanted to go further, do more work under ice, but those M&M shaped vehicles are not very hydrodynamic. They're not very efficient. So the idea here was to keep that ability to stop and hover and pause and move vertically up and down in the water column, but also get some increased range. So that was Artemis. And so the goal of Artemis was much bigger than little old Lake Bonny. The idea of this was to take the first kind of tentative steps for a robot to go underneath the Ross ice shelf. Now the Ross ice shelf is the size of France. It's huge. And so our first work there was just kind of around the margins of it. This really took us away from feature-based navigation. In those sinkholes, the walls are really textured, strange shapes. You can identify very clearly where you are in a map because everything is so unique. Under the Ross ice shelf, it's just kind of like this smooth undulating thing. The ocean floor is quite far away. This may be a lot more like what most of Europa will be like, right? So it's important to learn to navigate in these environments as well. But the trick here is most seagoing AUVs can pop up for a GPS fix if they really need it. And in this case, we were not able to. We did have to return to the one little hole that we had melted for the robot to come back at the end of the day. And in order to do that, we created kind of a multi-part, return to home and docking system. And this is the final stage of that, this kind of glowing light bar. These are, just a series of blue LED lights that would flash on a frequency that we do not believe, and much is unknown about the deep sea, but we do not believe that it is mimicked by any other kind of bioluminescent life form underwater. So this is definitely the docking bar. And so there would be a machine vision camera on Artemis that would be looking for that flashing blue. And then as it's approaching, you can tell by the spacing what it perceives as the spacing of those LEDs tells it how far away it is from the docking bar. And so it would come right up to this place and then capture it. And then we would use the bar to haul it back out of the hole. So I've got a bit of a video here, and I like to just kind of talk over it rather than let the music play. But Artemis was a really interesting time in all of our lives. This went from being a design on a computer screen to being a vehicle that was fielded in Antarctica in about 12 months, which is an incredibly rapid design cycle here. So this is a time lapse of us constructing the thing in our lab here in Texas. All kind of set and ready to go. Shipped off to Antarctica. We were based out of McMurdo Station. That's the volcano Mount Erebus behind us there. McMurdo is the largest US installation in the Antarctic. So there's all kinds of heavy machinery to help you out. As far as Antarctic work goes, it's you get all the big toys. We actually had to put that big culvert pipe in so that the hole wouldn't refreeze. We still had to chisel it out every day. There's the robot and its big crate being taken to the site. You can see how many people are involved here. This was a huge operation. Long range vehicle, but man, it was a lot of work. Artemis collected water samples in addition to doing these treks. We did some diving work with it. That's actually me getting ready to go in. The launch and recovery operation for this vehicle took about an hour and a half to 2 hours, every day at the beginning and at the end. And we were running 24-hour missions. So these became very, very long days. Of course, the sun never goes down in the summer there. So, so you just keep going. Underneath the ice, so this is under the sea ice, which is much thinner, maybe 5, 6, 7, 8 meters thick. And that billowy cloud that you see is actually this platelet ice, these thin crystals that are just kind of like accumulated underneath the hard ice. It was really cool. Here we're getting that data feedback, right? So this is sonar feedback from that relatively featureless environment. We were able to track from the surface through the ice where the robot was. In case it didn't come home one day, we could go and get it. And then here's that docking bar coming down, kind of from the robot's point of view. And captures the bar. So 20 dives. It was a long and busy season. I think it says here, yeah, the longest run was over 10 kilometers. Again, commercial AUVs will go farther, but they won't have the instrument package, and working under ice is very difficult. So really cool project, a lot of fun. We definitely learned a lot. But man, this thing is huge. It's the size of a minivan. And so when you talk about trying to take advanced technology and work in some sort of remote, unexplored environment, man, those two things don't go very well together. So we really wanted to take kind of everything that we had learned with underwater vehicles up to this point and create something that was much smaller. Now we had to give up some of the battery power. We had to give up some of the larger instruments that don't come any smaller, but we wanted to keep that high maneuverability. And what we ended up with was something called Sunfish. And this is Sunfish here in our test tank. This is kind of like the fighter jet of AUVs. So this is incredibly agile thing that can move very precisely. It's only got one mapping sensor on it, but as you'll see in a second, the ability to spin around like this gives it a lot of power. So we took this, we were talking a little bit about Jill Heinerth earlier. We took this to Peacock Springs in Florida. Peacock Springs is a flooded cave system, and it's fairly mazy. It's very labyrinthine. And that's really what we wanted. We wanted to really tackle complex decision-making underwater. And so this is a hand-drawn map. So we wanted to tackle obstacle avoidance, exploration, and path planning. How's the robot going to choose what it's doing? We had divers help us through this one little narrow section before Sunfish kind of went off on its own. I'm going to show you a video of what the data feed looks like coming back from this. And what you'll see is how Sunfish is able to, it has one multi-beam sonar on it, just one sensor for mapping. You'll see it's able to pirouette, and that mapping instrument sweeps across the walls and is able to fill in that sonar data. Let's see. So you can see how the vehicle is kind of spinning around, and those little dots that are appearing are where the walls are. Now, each time Sunfish does one of these scans, it then looks at the data and says, okay, within the walls that I just found, where is a space that is big enough for me to move? And that's the little white smudge that you'll see show up sometimes, is a space that it believes it can move. Within that space that it believes it can move, it will then choose the direction that best matches its objective. So in this case, we told it to go to try and get 200 meters north, and north is up in this case. So it managed to do that, got 200 meters north, and said, okay, it's time to turn around. Coming back, it's much more efficient because it can follow the map that it made. It does stop and double check, like, okay, am I really where I think I am? Let me look at the map. Okay, yeah, this matches the map, I'm good. And it's able to return home. So this was super cool, super exciting work. And this is the sonar map that comes out of that. And then if you overlay that hand-drawn map on there, man, hand-drawn underwater survey by cave divers is very difficult. I'm going to lay money that the sonar map is probably the more accurate case here. The work in Peacock Springs was really fun and really exciting and really kind of showed what we could do. But Peacock Springs is a place where people are cave diving pretty much every day of the year that there isn't a hurricane happening in Florida. It's a very popular cave diving site, and all of it is known and well explored. So the next step we really wanted to do was take it beyond diver recovery and take it beyond the limits of human exploration. And I came across a reference to this place that was still very unexplored called Dragon's Breath Cave in northern Namibia. And was able to get some funding from National Geographic Society and several other groups to run an expedition with Sunfish to this place. And once we started looking into it, there are actually a couple of caves in this area. So this is northern Namibia. And the cave we actually started with was a neighbor to Dragon's Breath called Hairseed Cave. And right now we're looking at a pit that leads down into Hairseed Cave. And you can see all these lines going across. You'll see in a moment how we use those to get stuff in and out of there. When we first showed up, this was what was known about Hairseed Cave. So the yellow section, again, we're looking at that inside the cake slice, we're looking at the profile view. The yellow section is air filled, and then there's water at the bottom. And it had been dived to almost 147 meters water depth, which if anyone's a diver, you realize that's significant technical diving happening at that level. And when I talked to these folks, I said, well, why didn't you keep going? And they're like, well, it's incredibly deep. And I'm like, well, where are the walls? And they said, you don't understand. We couldn't see them. I'm like, well, you said the water's very clear. And they said, no, it's that far away. It's that big. We have no idea. It's like being in the middle of outer space. So this seemed like a really great place to start with Sunfish. So we bundled Sunfish up in the rescue litter to get it into the cave, lowered it down through a neat series of pulleys and hoists and whatnot. Here's looking down that 112 meters, so you can see all of our gear laid out nice and tidy along the right wall on the bottom. You can see the lake kind of in the lower left, and then if you look hard, you can see the little orange rectangle that is Sunfish waiting to go on a mission here. So this shaft was incredibly beautiful. Just because it hits water doesn't mean it stops. It just keeps plunging straight down. This water is incredibly clear, and so we sent Sunfish off here. This is the first time I was ever able to see the vehicle as it descended. I always knew it was doing these pirouettes, and we were seeing the data come back all the time, like, oh yeah, it's spinning, it's doing its thing. This is the first time I was ever in an environment where I could watch it, and it was incredible. And we could watch it to incredible depth. It just got smaller and smaller. These are the 3D maps that came out of Aerospace Cave. So on the left is that profile view. It goes down very sharply. That green chamber was completely unexpected after that little pinch down point. Eventually reached a total depth of 387 meters. And then on the right is the top down, the plan view of what that place looked like. We almost lost the vehicle in this place due to a depth sensor error. So that was exciting, but very cool. With the depth sensor error remedied, we went off to Dragon's Breath, and Dragon's Breath was the main reason we were there, and it was much more challenging in several ways. The first was that we didn't have this nice big open pit with big pulleys to lower everything into. This is the entrance of Dragon's Breath. It has this little ladder in here you have to kind of squeeze down in. But once you get past all of this little narrow stuff in the top, you reach what is one of the largest underground lakes in the world. It's an incredible chamber. Again, this is a spot that had been dived to about 150 meters. And again, they couldn't see the walls. They didn't even know which direction to tell us to start. This is not a photo from my expedition, but a different group. It's the best single photo of how large that lake chamber is. So when you're on one end of the lake chamber and trying to talk to someone on the other end, you're using radios. It takes about 10-15 minutes in that little boat to paddle from one side to the other. I got lost in there once. I couldn't find the way that I had come in. It's so big. So, but to get in there, you have to go through this little fissure at the top of the chamber. Sunfish barely fit in, but here now you can look down and see again sunfish as you're first coming into that chamber, our little floating platform, the whole deal. We talked a little bit about this fiber optic line that runs to everything. We ran that all the way down into the cave. Kind of a pain, but definitely worth it to see the data as it was coming back. Again, just lowering the robot into the water, off on a mission, or launching for a mission in this one. And then since we're in Africa, there are a couple of things that I had never encountered in field work, and one of them was baboons. And so we had left everything strung up overnight, and we came back and the fiber was no longer working. And we think the baboons had been curious about it and broke it. So we had one of our technicians do a field retermination. Normally this is done in a clean room or at best, a clean building, but he's gotten quite good at improvising with that. So with that all repaired, we were back off on the mission. The little game controller here is just for the starting checklist before the mission. And here's the map of Dragon's Breath. So on the left is the top-down view. If you can see the little black line, that's the outline of the air-filled chamber where we're paddling the boats. That giant chamber is only the section that's within that little black line. The full extent, the full horizontal extent of the cave is much, much larger. It's incredibly huge. As a person who loves exploring caves that are not water-filled, I wish I could have been able to walk down through this place. On the right, is the profile view. You can see it goes down this big slope. Now, when we first started here, there was the potential that this cave was going to go for tens of kilometers. There was the, some speculation that would be the case. It was a little disappointing that isn't what happened, but caves do what they do, and this one ended. So this is a quick little 3D spin of how that came out. The little red fin at the top is the air-filled section that you had to rappel through with all the little cracks and stuff. So at this point, it starts to feel like, wait, weren't we talking about Europa? Weren't we talking about robots in space? She's kind of gone off topic here. And I kind of feel like I have, but I haven't. So this is again in Dragon's Breath. These are all strange environments here on our planet. It's an incredible privilege to work in these places, but they really call on things kind of deep within us as humans, as explorers, like how do we tackle this problem? And then how do we convey that into something that a robot can even begin to start to duplicate, how we might explore some of these places. And that happens under ice, that happens as we're going through ice, that happens underground. So maybe this isn't exactly a Europa situation, but some of the navigation challenges are the same. And some of the spirit of the exploration is the same. And I like to always kind of like go out on a bit of a philosophical note here. And I always enjoy updating this slide every time I give this, maybe once a year or something. And as of a couple of days ago, we're officially at 5,000 confirmed exoplanets outside of our solar system. And we talk about how many ocean worlds we're still trying to figure out which within our own solar system, which worlds are ocean worlds. And then you look out beyond that, and who knows what all of these worlds are going to be like. And if somehow we're ever able to send robotic explorers or even humans out beyond, we're going to lean so heavily on everything that we've learned in Earth exploration, terrestrial exploration, all these weird caves and glaciers and under ice shelves, all of this, it's all going to come into play someday, I think. And it's kind of neat to wonder and speculate and just never know where some of this work is ultimately going to end up far in the future. So that's what I've got for slides. Thank you for listening. I know it's a long one, but I'm happy to take any questions.
Yeah, Vickie, when you started talking about the cryobots and I saw them going down, I wondered about the ice forming behind them. That is, the water, as you melt it, refreezes above. And I think you repurposed the idea in terms of sealing, so it causes pressure. But I'm wondering, in terms of a 20, 30 mile descent, I mean, thoughts at all about actually managing the water as it refreezes? It seems like you would go down a cylinder and you would end up with a cylinder frozen above you. So just in terms of practicality of actually then launching an AUV and recovering it.
Yeah, so the cryobot is probably going to be longer than we want it to be. Like ideally, for purposes of melting ice, you want a cylinder that is as narrow as possible. You want a small diameter as you can get. Of course, the smaller you make the diameter, the longer you make the vehicle, because you still have to fit all the rest of the stuff in there. So once you start to get a very long cylinder, you get really far from where you've been melting or drilling or whatever you're doing. And yeah, there is a concern that you're going to freeze your tail in the ice behind you. And so the idea that we've had is to run some sort of heating, be it heat pipes or, a resistive heater, something up into the rear shell. And this will change over the course of the mission as the temperature profile of the ice changes as we descend. How much you're going to need that rear heating is going to change. But the idea is, to keep that stuff heated so it still has a thin film of water that can lubricate on its way down. The other idea that we've played with especially with terrestrial systems, there's some overlap here where if we get good enough at cryobots, these could actually become tools for investigating subglacial lakes in Antarctica. And in Antarctica, they definitely do not let you abandon things, robots. It's supposed to be kept a clean environment, right? So in that case, we've actually come up with the idea of creating kind of a reverse winching system that's built onto the vehicle. So you have some sort of very strong tether that's tied off at the surface. And then you're slowly winching yourself down, and then you let the ice refreeze behind you, fine, whatever. And then when you come back, you actually have heaters or possibly reverse jetting on the tail of the cryobot, and you're pulling yourself up against the surface of the ice with your winch, and you're heating and you're melting your way back up out of the hole. There's not a lot of use for that on a Europa concept, but I think terrestrially we might see that someday. And then as far as launching the AUV and the cryobot into European ice, that stuff is all going to be, none of that is going to be recovered. That's not kind of in the works. Yeah.
Well, so just to take that a step further, then when we talked about the fiber optic, so there won't be a fiber optic, and it goes down, but the data is in the bot itself. I'm just wondering how you guys project at recovering the data from the AUV now buried under 3 miles or 30 miles of ice.
Yeah, so this is stuff that's new enough that I don't have it in the presentation yet because we don't have anything official to report or anything. But this is a very interesting topic of research. So there are people who are proposing to run that same fiber optic line down the whole way. You can get very thin fiber, you can wind it quite tight, you can get On sunfish, we have a disposable fiber that you can get 4 kilometers in a spool that's about that big. So you can, theoretically, you can fit enough fiber onto a cryobot that you could get through 10 kilometers, 30 kilometers of ice. The problem is, what we're all worried about is that brittle layer shearing. We're worried about that cracking and shearing and having some sort of like fault slip and break that fiber. So there are groups that are looking at like, well, what if we make a really strong fiber? What if we do this to the fiber to give it some strain relief? We're working on a backup communication system where you're actually using radio frequency to transmit through the ice. There's a lot of problems here, but the idea is that you would have a series of deployable, for lack of a better word, pucks, little transponders that as the cryobot's descending, every so often it releases one of these things and it freezes in the ice and it stays put as the cryobot continues to descend. And so it would have a much lower data bandwidth, but you could get something back out through this kind of string of breadcrumbs that you leave behind. So we're working with that. We're hoping to take a couple samples into some very deep moulins or pits in the Greenland ice sheet in a couple of years and do some preliminary through ice transmission with that.
Yeah, I would really encourage you to tap into the oil and gas business. Everything from ROVs to drilling through ice. I know it's slightly different, but if you have technology that they could use, that would be a really big source of funding.
It's true. It's true. And we just, yeah, I feel like we haven't really gotten to the maturity in the technology, I guess, that we have anything to really bring into that conversation. But I think at some point, definitely that crosstalk is going to happen.
I'd like to riff off that a bit.
Yeah.
I work for the Geological Survey of Canada, and we are very keen to get involved with unmanned vehicles for studying the seafloor. We're putting a lot of work into it, and we're still talking about just a few hours of battery autonomy and very light payloads. And I think one of the things that I just love about my amateur astronomy hobby next to my my profession is how each is helping develop the other. I can see components in your amazing AUVs that are just like the ones that we're using on ours. And I'm sure there's going to be technology transfer as you are pushing it because of your crazy engineering criteria that are going to be put back to normal civilian engineering. And do I understand that this is not part of your business model? I would have thought that that is the where you could actually finance, again, some amazing engineering that you just showed us.
Yeah, so we're kind of a weird group, and we so we're founded by this fellow named Bill Stone, who is a very avid cave explorer and has been for many decades. Kind of in the small world that is cave exploration, he's fairly well known for it. Also very interested in diving technology. Our whole goal here, we draw folks. The folks who work here could be theoretically working at Google and making a lot more money. But the thing that kind of brings people here is that we have this idea that we just really want to do things that are interesting and cool and take us to interesting places. So we're working largely off of NASA research grants from other federal institutions, occasionally a private project here and there, or I ran that one expedition through the National Geographic Society. So we kind of find these unusual, honestly not particularly lucrative funding sources to drive the technology and take it to cool places. With sunfish, however, we have advanced that to a point where like, okay, this little baby is ready to fly. And so we've actually spun off a separate company, a separate enterprise called Sunfish Incorporated. And that is focused on using that vehicle for inspection purposes, either for infrastructure or for, you know, science and exploration, that isn't completely, you know, take a prototype and take it somewhere weird. It's like, okay, we have a more mature system. We can do things like pier inspection or ship hull inspection, or, you know, collect scientific data. We're going to be going actually to Devon Island in the Canadian Arctic in 2024 as part of a science project, but going underneath ice. Again, it's a, you know, it's kind of a boutique job, but, you know, survey with an unusual instrument in an unusual place. So that's, yeah, so we have kind of made that final step into like really trying to commercialize things, but really our heart kind of stays in this, I don't know, think tank, robot, cool shop space. And we keep going with it. We keep staying afloat with it. So it's been 15 years or whatever. So it's working out. Sorry, I don't know if I started to ramble. I don't know if I addressed your question.
No, it's spot on. I mean,
Okay.
they're building off each other, and it's clear that that's what should happen. And it's what's always happened for hundreds of years between astronomy and civil engineering.
Yeah, I'd really like to see a point where we're able to make the cryobots useful in terrestrial glaciology. I think there are a lot of applications in the in the Antarctic and Greenlandic ice sheets, where we could offer a really good alternative to traditional hot water drilling solutions for science studies, but we're just not quite there yet.
So I see Leslie has a question, and we have one from Lori on the chat.
Vickie, you have got to have one of the coolest jobs that's ever existed. It's just incredible. Surely Stone or NASA has realized the potential to make a fun documentary out of this, and we'll be seeing it on the Discovery Channel soon.
There are a couple. There have been a couple in the past. So if you look, I don't know if they're online anymore. I could try to find the links and send them along. But there was one that was like Journey to an Alien Moon or something that National Geographic did on the Endurance project, the AUV that went to Antarctica for the first time. And then they updated that a couple years ago. We did a short video about the sunfish work in Namibia. But yeah, it's been a while since we've had a large film crew with us. Honestly, it comes with its own, whenever you have a film crew around, all of a sudden everything goes a lot slower. It's kind of a mixed bag. It's like you want to document it, you want to get some excitement, you want to feel like you were in a documentary, but day to day working with a film crew can be tough.
Well, listening to you in person is way better than any documentary, but I would certainly want to see any documentaries that exist. Thank you so much.
It's very flattering. Thank you.
Hey, Lori, why don't you ask your question?
Sure. So, Vickie, you're talking to a person who doesn't take very many risks in life. So my question to you would be, have you ever been really honestly afraid working in any of these situations, in these environments, and where you thought your life might have been in danger from some of the things that you were doing down there? And what did you do to help yourself through those moments?
Yeah, it's an interesting question. So the answer isn't specifically related to robotics, but as we've kind of been talking, there's a lot of crossover, and whatever you learn in one area of passion and focus has a strange way of crossing over into the other parts of your life, right? So I first got this job because I'm a caver, I'm a cave explorer, and I had been working in Mexico. And the company founder is a cave explorer, and he had been working in Mexico, and he had just started his company and said, hey, I need somebody to help run operations in Mexico. I've got a bunch of engineers who have never been and don't speak Spanish. And so all of a sudden there it was, and that's, long story short, I'm still here. So my answer actually comes from the caving side of my background. There was a time in 2009, I was on a multi-month expedition to a very deep, very complex cave that we were exploring, again, in Mexico in the state of Oaxaca. And the portion that we were in flooded, and we were trapped for about a week with very little food. There were 7 of us. And ultimately we ended up having to dive out with very limited dive gear, and I'm not a cave diver. So that was very, very scary and very challenging. And so what did I do to get through it? It was interesting, really working just with focus and not giving into emotion for a couple days, and just really having, slow, deep breaths, a lot of focus. And I've since gotten really into yoga in my life, and that really kind of helps that practice. Honestly, it sounds silly, but it's very true. Everything they say about mindfulness. But I will tell you one thing, Lori, after that experience, I had to testify in a completely unrelated court case about something. And the guy was trying to make it sound like I was an incompetent technician, and no way could I have taken that bolt off properly because I'm a woman and whatever. And after the experience I had just been through, it was like nothing. I was like, I'm in the sunshine. I'm going to live. You don't have anything on me. Everything in life for years after that actually seemed much easier.
Oh, that's good. Thank you. Thank you.
Yeah.
Reg, you had a question? I see your hands up.
Yes, thank you. First of all, thanks so much for a wonderful talk. I very exciting. It's kind of you're channeling both Jules Verne and Indiana Jones in this thing. It's just great. You mentioned the project for the Clipper mission going to Europa, and I was wondering, are they planning to have some sort of a sounding system at all to try and determine what the depth of the ice might be on the planet?
That is like the number one thing we all want to learn from that mission. So Europa Clipper, it's actually an early model of it is on this thing behind me on the wall. Europa Clipper is supposed to launch, these things always slip, but it's supposed to launch in 2024. It's supposed to get out there about 2030 and spend 3 years making kind of these like zippy little flyby passes. Again, the radiation environment around Jupiter is really going to wreak havoc on this thing. But the main thing they want to do is deploy an ice penetrating radar that they've been testing in Antarctica for years, flying over with DC-3, Basler aircraft. They have this ice penetrating radar. And so they want to see, that's the main thing they want to see is like, how thick is the ice? How thick is the ocean? Can we tease that out of it? There's a number of different instruments on there that I should probably be better versed with, but I'm not. But we've worked with that ice penetrating radar team a bit. That was one of our collaborators on that Artemis project. The idea was that Artemis would go underneath the Ross ice shelf and map from underside and provide ground truth for the ice penetrating radar overflights. And that's some of the work that we're going to be doing on Devon Island as well, is related to proving out the instrument that's going to be on Clipper.
Amazing. Thanks very much.
Yeah.
If there's no other questions, then Vickie, thank you so very much for taking the time and giving this talk to us. The innovative use of technologies means that we're, I think, going to be hearing about Stone Aerospace for many years to come. Thank you very much.
You're very welcome. Thank you for inviting me.
Jeff, I think Peter has got his hand up.
Oh, I missed it. Sorry, Peter.
Hi, good evening, and Vickie, thanks. Excellent presentation. Before I ask my question, Reg mentioned Indiana Jones, so I'm going to mention my favorite hero from my childhood, Tom Swift, book number 5, Tom Swift and the Atomic Earth Blaster.
Oh, nice.
They sent a vehicle down below the ice in Antarctica, and they discovered a huge pocket of molten iron, which of course made him richer than Elon Musk. And that's how he funded all his later space explorations. And if you're 10 years old, that's a fantastic thing to read. I don't know if 10-year-olds today would feel the same way, but I sure hope they do. So my question is on Europa, you've got all those famous cracks, and even the one diagram you had that sort of showed the side view through the ice features. You know, the ice is 30,000 meters thick. Why not just send a vehicle through one of those fissures? Is that harder for some reason, or wouldn't it be easier? It's already broken or possibly even liquid.
Yeah, no, super good question. And it's just not something that there are groups that are looking at this. And I know at least of one or two again at NASA JPL. And usually when folks have this conversation, they're usually talking about Enceladus. So Enceladus is a Saturn satellite. It's a good bit smaller than Europa. But it's got these plumes. So we're regularly observing these plumes. I think maybe Cassini even flew through. Some of you guys probably know better than me. And it's got this region called the Tiger Stripes, which are thought to be these deep fissures. And so folks do talk about sending robotic systems down into that. It's just I hate this expression, but it's just a different way to skin the cat, right? So it may be easier in some ways, and it may be more difficult. It's in some ways, it's very simple to just kind of like hunker down and slowly melt through ice. It might be faster to kind of rappel down, or like have some sort of robot that can like spider leg down, or all these different, climbing robots or ice screw drilling robots, all these things. They all have their challenges. There's no free lunch. So folks do look at that. One thing that comes up with those discussions also is like, well, if you have these plumes ejecting out, like, why are these cracks there? Why are they maintaining? And is it because there's some sort of infrequent yet dynamic process that is kicking things back out? And if you try to rappel down, are you just going to get, shot back out into space? But it's definitely an avenue that folks are looking at, and it's just not, we don't have the bandwidth to go each direction. And I'm kind of agnostic as to which is going to ultimately be the best. But it's everybody's job to investigate all of them, right? So thank you for the Tom Swift reference. I try to collect kind of Antarctic stories and true accounts and fictional accounts and all that kind of stuff. So I'll look for that one. Thank you.
That's my favorite. I'm pretty sure it's book number 5 in the series from the early 1960s. And even the
Awesome.
cover. In fact, if you give me a moment, if the meeting continues, I'll share screen. I'll show you what the cover looks like. It's pretty cool. Thank you.
Cool, thank you. Yeah.
Thanks again, Vickie.
No problem. Do you guys mind if I listen through the rest of the?
No, you're
Oh, no,
absolutely.
you're more than welcome to stay. Please do.
Cool, thank you.
Great. Well, and I'll echo that. Thanks very much. That was fascinating. And hopefully we'll, get to see some more happening, and with the next round of missions and things. And it'd be nice to see what happens when you come up to the Canadian Arctic to see how it works. Very good.
Thanks very much.
So Randy, you wanted to say a few words tonight, I believe.
Yes. Let me share screen. Okay, first of all, a little bit of the fun of astronomy. So there have been a couple of times I've got to see the moon in the last couple of weeks, which was better than the month before. This was on the 20th. And the cool thing with this one, I mean, it's Cleomedes was my target next to the Myricrisium, very nice part of the moon. But as I was doing it, this star came out. It was the, out of the dark, past the terminator, it just appeared. And I looked it up later. It was about 10 minutes before that it came out from the moon, and it was a magnitude 5 star. So next to the moon, it would not be visible even with a very dark sky because the moon was right next to it. But it's the first time knowingly that I could see that a star came out of occultation as I was staring at it with the telescope. And that, I don't know, just one of those really nice feelings. But yeah, there we go. Just wanted to show my note of it. And then it was my birthday and my kids got me a new set of sketching pencils. These are Staedtler 2mm leads. And so just wanted to show you my birthday present to myself at 5 in the morning on Thursday. And this is way up at the North Pole of the moon. And what got me is how square the craters looked. And just to compare, this is what the Lunar Reconnaissance Orbiter would have seen at that same time. But yeah, the more you look at the moon, the more you see. That's my little note. Anyway, now for some announcements. And I guess in chronological order, let's start with Dorothy, because in a couple of weeks is the Vancouver Island Regional Science Fair. We are still online, but it's going to be our own local fair. And Dorothy for years has been leading our efforts to award the top prizes in astronomy. So Dorothy, do you want to add something right now?
I just wanted to encourage some of the new members to think about being specialty judges. It's a lot of fun. This year, there are only about a third the number of the last in-person Vancouver Island Science Fair. So they're only a little over 50, but I got an advanced list of the titles, and the proportion of ones that are potentially excuse me, interesting to us is high. I actually marked, I think, about 8 that I out of 52. Some of those have to do with light, and biology probably wouldn't be appropriate. But the point is so much fun to talk to these students. Most of them are this year are between 5th and 9th grade, kind of the middle level, and they're black holes, rockets, space junk, moving the sun, light at night, various topics that it's worthwhile talking to the students, and it's possible to, even if their approach does not overlap at all with our interests, which are in light and all aspects relating to life on Earth and in space. And it's possible to kind of suggest things that they might have thought out if they haven't. The projects can be just studies, which are basically like a review and a neat posters sometimes, to experimental engineering, and it's a great fun. And it's just Vancouver Island this year. Back last year, we didn't do it because it was a much larger region up to the Yukon, and it didn't seem at all practical or desirable. So if anyone's interested and would like to hear a little more than what I think, Randy, you're going to be sending us around, or there will be more in another week or so, the kind of finalization of the details for the fair. But if anyone would like to know a bit more what it's like, you could just email me and I could give you some tips on, encourage you. It's next year, hopefully we'll be back in person, and there'll be a more typical number of students from 4th to 12th grade. And we've had prizes from 4th to 12th grade in the past. So let's hope.
Thank you, Dorothy. Yeah, so we want a couple of people that will go and interview the 8 or so projects And so we'll talk a bit more about this at council tomorrow. So that's the next thing is, yes, there's a council meeting tomorrow, and we'll talk about that. We'll talk about the approaches towards making Astro Cafe hybrid, and we're making great movement towards that, and they'll just, stay tuned. And big thing is May 7th. So just over a month from now is International Astronomy Day. And we will participate with the Friends of the DAO and all the other astronomy organizations in town. We'll talk a bit more about this at council tomorrow. Lori, do you want to say anything right now, or just know that we are going to be looking for volunteers?
Yes, hi. It'll be lots going on. Just for your information, is the FDAO is giving a proposal to the NRC for actually opening in person on the 7th of May. We have not been given, permission totally and everything yet, but it's further along than it was 2 weeks ago. Let's put it that way, that we'll actually be in person up there, and that we'll have something in the evening. We absolutely want to have something during the day at the center as at the museum as well. And then there also is going to be this cross Canada kind of webinar happening, like across for the different centers during the probably kind of in the afternoon, or like our afternoon and their kind of evening across Canada, for dropping into the centers and finding out what's happening across. So we can probably get ourselves organized for about 10 or 15 minutes worth of some either live viewing if it's absolutely gorgeous out, or some sort of little bit of some things that we have done before, or what's going on. We can kind of come to something. We've got about a 10-minute presentation that we can be involved in for that program. So, and
in our proposal, we have insisted on clear skies that night, right?
Okay, absolutely. Yeah. But
okay, good.
Every now and then, sometimes they don't listen. So anyway, there's lots going on. I'm looking forward to tomorrow, where we can sit down. We can kind of get some things organized and get some programs going. So that's great.
And the last thing I want to say is back to the Astro Cafe. It's been a lifeline for our community for the 2 years. We want to see it only get better, but we're going to need a bigger volunteer base to operate the hybrid model. It's we've under Joe, in this very nicely constrained setting, it has gone up in our production standards and are getting it onto YouTube and all that. We want to continue that, but we need a volunteer base to be able to pull that off. And the threat is, if we don't get 3-5 people, we're going to share the load. It's not going to be as good. So if you love this Monday night thing, which I think many people do, we're getting 30 people every week. We need to have some people who will put in some time, much like we did when it used to be in person. People have to set up and things, but please contact me, contact Chris, and let's get a group of people who can work together either on site or on the Zoom, because we're going to need people offsite also to monitor questions and things. So volunteer, it makes it better for everybody. And I'm out.
Thanks, Randy.
Randy, is it too early to know what it is that will be needed?
Well, we need people to be hosts. So people to, get the evenings organized. So when we're back in site in Fairfield, the room has to be set up. There's put this stuff on, organize, and, kind of chair the meeting. And then there's the main function, of course, of what Joe's doing, which is behind the scenes to make sure that that we're integrated with Zoom. So we need people who can sit at a computer, monitor what's going on for the people who have signed in on Zoom. And basically that person will likely be the person who will show the things in the room. Right. So when we've, in the past, we'd have people come and it was just in the room. We didn't have the Zoom part before. So now we want to keep the Zoom part as well. So there'll be some people sitting in Fairfield and then some people at home. And so we need, as Randy said, we definitely need people to be the talking head in Fairfield. I can't be there every week. There used to be, there were 3 of us before. Well, it was 4 really, because it was Kurt and Barbara, John and me. And it's down to me at the moment. So I'm the only one doing that. And then Joe stepped up to do this volunteer without being asked to take on doing this function with Zoom. But he can't do that all by himself, and he's not available every week either. So I don't know if you want to say a few words about what's actually involved, or not. Sorry, Randy, you were going to say.
Oh, I was just going to say there's going to be 2 big screens, one for presentation, one for the people. It's a lovely room. It's a different room. It will have adult-sized chairs in it and couches. It's just the next part of the building over from where the kiddie place was. So, we'll still park in the same place. There's good access if anybody has trouble with stairs. It's lovely. It will serve us well. And the people at Fairfield Gonzalez Community Association are wonderful.
Yeah, they're really going all out to make us welcome. So basically, I would say those are the 2 kind of the main roles we need. Somebody, a hosting team, and then a Zoom team.
Yeah.
And probably.
And the Zoom is not difficult, but it just requires someone to be there and probably aim the camera a little bit now and again and make sure everything's working. It's not technically challenging. It's no more challenging than what you're doing sitting at home, watching and participating and speaking and all that sort of stuff. You have to click a few buttons once in a while and keep it going. We have a good, strong internet connection from this room, so we should be able to carry the video signals back and forth as required with the dropout. So it's looking good.
Yeah. So I would say we're looking at probably, 3 people in each group minimum, I would suggest. 5 would be ideal in each group. So 10 people involved in this would be nice. Means you do about one night a month. So anyways, yeah. So I mean, more discussion for those who are on council. We we'll talk a little bit more about what we Randy, Joe, and I were there. What was it, last week, I guess, and had a look at the facility and tested the network
on Wednesday.
Yeah. So we'll report back tomorrow. Great. Well, thanks. So we have something from Edmonton, a little bit different this week. So Dave Robinson, if you're ready, I will share my screen. First of all, though, I will show, this is Peter sent this is the book that he was referring to, and he shared a link to the atomic earth blaster itself. So I thought I'd just pop those up. Those links are in the chat if you would like to see them some more. So the book, and there they are, and his atomic earth blaster. So there we go. So this is Stone's newest design to take care of that. Very good. Anyways, on to Edmonton. Let's see here, where are we?
Okay, so yeah, Edmonton has been snowed and clouded pretty badly, so they've been doing other things. One of the things that some of the members have done is taken up a challenge to observe an object they call the Deep Sky Object of the Year, which is NGC 2022. And if you look from Sky Safari Pro, and you've got another couple of, this is the actual, that's like a Hubble shot of it.
Yeah, that's the Hubble shot.
You're not going to see that with your naked eye. But if it's located in Orion, it's roughly, it's directly aligned directly between Betelgeuse and Mesa. It's about a third of the distance from Mesa towards Betelgeuse. It's pretty small, it's faint, needs a good dark sky. It's going to be challenging for us to try and find it because it's low in the west when dark enough, and the horizon might interfere. Now, gave Chris a couple of screenshots from Sky Safari.
I was just going to say, it's just interesting. I thought that looks almost a bit like an X-ray there, kind of ribs and stuff. I thought it's kind of interesting thing, anyways. But yeah, we won't see that. Anyways, this is the your first.
So this is I've put in my 10-inch scope criteria, and that's kind of what it would be like in my 4.7 millimeter eyepiece in my 10-inch Newtonian. So it's not very big. But if you were not to find it, it's fairly straightforward. If you push the next button, the red circles are the Telrad circles, and you can see Mesa on the right and Betelgeuse on the left, and it's about a third of the way. So if you were to put the Telrad circle right on Mesa, you're going to be awfully damn close to where it is. It's a little bit above the straight line. And then I would suggest you use a wide field eyepiece to get the star background kind of right. And then you might want to try a little higher power to darken the sky, see if you can actually see this thing. A couple of guys in Edmonton have seen it. I think Abdur and Cochrane saw it, but then he's got an absolutely dark sky there. So it might be something if you want a challenge for the short period of time that Orion is favorable, you might want to give it a go if we get some nice clear skies.
And this is it tonight in about 10 minutes.
That's where it is tonight. Yeah.
Great. Thanks, Dave. Great. And I think Dave Payne, I think you had some things you wanted to.
Well, I'll offer to keep my powder dry, just seeing that it's we're over time. So it's up to you.
Did you had a couple of images?
Yeah, just a couple, I guess.
Oh, we could see them. Why don't we see them?
Okay.
They're always interesting.
So am I sharing?
Yeah, it's there.
Okay. A little bigger here. So this was just an image I took a few days ago. I thought it was a really interesting galaxy. Took it from the backyard. It's the Hamburger Galaxy. But it was very interesting for me because it's edge on, but I was looking at the atmosphere of the galaxy. It was really big at the end, and although it's called the Hamburger Galaxy, it looks more to me like a bone, X-ray of a bone or something. But I thought that was a really interesting shape. And if you look closely at the dust lanes, it's almost like it's on two planes forming an X. There's one plane and there's kind of the other plane. And I always like these pictures because, you know, when you look at them for a while, you keep seeing tiny little galaxies here, and there's a really nice one right up in the right-hand corner here, offsetting a star, and you just keep finding more and more galaxies in them. But so that was a fine little endeavor I had. But I also, and I started doing my taxes today, and I got fed up with doing that. So I took some of Dan Posey's Plaskett data, and so this is going even quite a bit deeper, maybe about 100 times deeper than my backyard scope. And this is of the Hickson 44 galaxy collection. So it's these are pretty small, even in my telescope, but the Plaskett is got a nice big mirror, and one of the galaxies that was in this data, it's not quite edge on, but it actually showed the very same similar thing that I saw in the previous image. It's like it's got dust lanes on a couple of different planes, and there's right at the edge of the galaxy, the atmosphere tends to bulge out. So I just thought that was really interesting, and I don't know what that says about the dark matter or the structure of the galaxy. I'm just gonna keep an eye on it going forward. And then again, similar, it's like almost a fractal type thing with the different size telescopes, because you can zoom in and you can see still really tiny galaxies. There's one here, there's one here. You see all these galaxies deeper still. So it's just interesting how you just change the scale completely, but you see the same thing. Anyways, that's enough.
Well, thank you. Well, thanks again for attending, everybody, tonight. Does anybody have any final words, or are there any SIGs this week, David? No, I should have asked.
I don't think so.
I don't believe so.
No, okay, so basically council meeting tomorrow night, and then it will be April. Quite a thought. So anyways, yeah, and we'll look out for information about our upcoming Astronomy Day, and if we can start having the Saturday star parties in person again, we'll be probably looking for some sidewalk astronomers. I guess we'll have to see how that plays out this year. How many people can, I guess we may have to control numbers. We'll have to see what happens, I guess. What they tell us, Lori, I guess is, well, just run with it, yeah. And thanks again to Vickie Siegel for joining us this evening, and all the way from Austin, Texas. And that was a very interesting talk. That was something I knew, I think I said at the beginning, nothing about. So I learned a lot, and thank you again. And thank you, everybody else. And we'll see some of you tomorrow night. And if not, we'll be back here on Monday. Good night, everyone.